Okay, so today we are going to work on this problem. It's problem 4.35 from the book. Here we are given a BJT circuit, and they are asking us to calculate the maximum value of RC if the collector base must experience a forward bias of less than 200 millivolts. They are giving us the reverse saturation current of the transistor, the early voltage, and the beta value, right? The book is also telling us that we can assume that the transistor is operating in the active mode. So let's start with that. Let's indicate that we are working on active mode for this case. Okay. So the first thing we can do here is, well, we have to take into consideration that if we want to assume active mode, we have to remember that the base emitter voltage has to be around 0.7 volts, which means that it is forward bias, right? Forward bias. Okay, and also the voltage at the across the base collector junction has to be reverse bias, right? Or less than 0. Reverse biased. Okay, a couple of equations we can use for this problem, since we are working on in the active mode, are the collector current equation, which is IC equals reverse saturation current times e to the power of base emitter voltage over VT. We can also use the active mode relationship with the base current, which is IC equals beta times IV, right? Well, we also have to remember that VT equals 26 millivolts, right? We can use these expressions without any problem. Okay, something to notice here is that we're given this value of the early voltage, which is infinite. And well, in reality, the current at the collector of the transistor is given by this expression, right? IC equals IS times e to the power of base emitter voltage over VT times 1 plus collector emitter voltage over early voltage. This is the real expression, but since you're telling us that the early voltage is infinite, then this expression will tend to 0, and all this expression will tend to 1. So yeah, this is not considered, and we're just working with this part, right? So that's a good thing. It makes this problem easier. Okay, so let's continue. So first, let's identify the current in this transistor. The base current is flowing through here, right? Base current. The collector current is flowing through here. I see. Since, well, this is the base, this is the collector, and this is the emitter, which is tied to ground. The current is flowing through this resistor, the base current. So this is a positive terminal and negative terminal. The collector current is flowing through RC. And again, this is a positive terminal and the negative terminal, because the current is flowing from top to bottom, right? In both cases. Okay, so first we have to consider that the collector base must experience a forward bias of less than 200 millivolts. What does that mean? That means that so we have this NPN transistor, right? Let's draw it here. We have this NPN transistor. It's divided in three sections, right? NPN. This is the collector. This is the base, and this is the emitter. So they're telling us that the collector base must experience a forward bias of less than 200 millivolts, right? So the collector base junction will be, collector base will be this junction, right? This PN junction. So that means that this PN junction has to be forward biased. That means that the voltage here has to be greater than the voltage here. So in that sense, we can say that the voltage across BC, so the voltage at this point with respect to this point, has to be less than 200 millivolts. So this has to be less than 200 millivolts, right? This ensures that the PN junction is forward biased since the voltage here is greater than the voltage here, and still fulfills the initial condition, right? That the problem is giving us. So, okay, this is our first assumption that we can work with to solve this problem. Let's mark it here. BBC has to be less than 200 millivolts, right? Which is equivalent, say that BBC has to be less than 0.2 volts, right? And let's call this equation 1. This expression, right? Equation 1. So this is our first expression we have. We can also identify and say that actually this condition, in order for a transistor to be in active mode, these two conditions have to be true, right? So this can be easily identified by solving the circuit, but it seems that this condition is not the same as this condition, right? If the problem is telling us that the voltage should be, that the BC voltage should be less than 200 millivolts, and this condition is telling us that the BC voltage has to be negative, it's like contradicting, it's contradictory, right? So, okay, the explanation for that is that actually when the BC voltage is less than 200 millivolts, it means that the transistor, that the junction is like a reverse biased junction. Why? Because it is not equal to 0.7 volts. The junction is not fully on. That the diode in this junction is not on because the voltage across the BC junction is less than 0.7 volts. And it's very close to 0 and to a negative value, right? So it behaves like an active mode. It has not reached, it is not in deep saturation. So we can still work with the active mode equations despite the BC junction is kind of forward biased instead of the truly reverse biased negative value, right? Okay, so we can safely work with that. Okay, so let's call this equation 1. We will use that later. Well, let's put it in this color. Okay, so how can we keep approaching this? So for example, we can, well, what we have to do now is that we have to find, we have to find a resistor RC, right? So if we only have this expression, which is the only condition that has to be fulfilled, it means that we have to find a BBC value in terms of RC in order to solve this expression, right? With only one variable. So our objective will be to find a BBC value in terms of RC, right? So in order to do that, the first thing we can do is to do a KVL. We can do a KVL right here at the transistor, right? Following this loop. So let's put here KVL1. KVL1. So we have to follow the loop, right? So it starts here, BC plus CE plus EB equals 0, right? So voltage across the base collector junction plus voltage across the collector emitter junction plus voltage across the emitter base junction equals 0. And this is equivalent to say BVC plus BCE minus BVE equals 0, right? I am doing this because the BE value is way more simpler to work with when we are working with NPN transistors. Since, well, we have it here, for example, right? We don't have to make any conversion. Okay, so this can be simplified. Well, we can isolate BBE. And BBE will be, no, sorry, we can isolate BBC. And BBC is equal to BBE minus BCE, right? And we can call this equation number 2. Okay. So we have expressed BC values, the BC variable in terms of BVE and BCE, right? But we still want these two variables to be expressed in terms of RC. So we have to find each of these variables in terms of RC in order to solve this expression one and get the final answer. Okay, so let's work one by one. So let's start with BVE. How can we find BVE in terms of RC? Let's look at the circuit. So, well, we'll have to work with this voltage, right? With this junction. So one thing we can do is to do another KVL, right? KVL number 2. And this KVL will go from this ground all the way crossing this resistor, crossing this junction, and to ground again, right? We have to follow that path, and we can work with that, right? Okay, so let's start. Following this loop 2, it will be minus 2.5 volts plus, we are following this path, right? Minus 2.5 volts. Now we need to pass through this resistor, which is plus the resistance RB times the current flowing through RB resistor, and that will be IB, right? And then we have to follow this arrow and go through the BE junction and to ground, and that is the end of the loop, right? So plus the voltage across the BE junction equals 0, right? According to the KVL. Let's put here that this is a KVL 2, right? KVL 2. And this is to find BVE. Okay, so yep, we have this equation. Let me erase this thing to avoid confusion. Okay. Okay, we now have this expression, and we can keep working with this. So let's replace some values, okay? Let's plug in some values. So it's minus 2.5 plus RB times IB. And well, if we use this expression here, that only works in the active mode, we can get the value of IB in terms of IC, right? Since we usually don't use IB that much in these equations. We have IC here, right? So we have to express everything in terms of IC. Okay, since IC equals beta times IB, that will mean that IB equals IC over beta, right? Okay, plus BVE equals 0. Let's keep working with this. So minus 2.5 plus RB, and RB is 100 kilo ohms. IC, we don't have IC yet. Beta is 100, right? According to the problem, right? This is given by the problem. Plus BVE equals 0. Okay, so we have this next expression. Let's call this expression 3. Okay, let's highlight this. This expression 3, right? So let's keep working with this. So we have already found BVE, but it is not in terms of RC as we wanted before. It is in terms of IC. So we need to find IC in terms of RC, or we just need to find the value of IC and express this voltage in a constant value, and that will also work, right? And to do that, we can actually just use this other equation for the collector current by doing another KVL. No, sorry, not KVL, just using this equation, right? So let's do that. This is point 1. Let's work on point 2. The collector current of the transistor equals to reverse saturation current times e to the power of BVE over BT. Right, so this would mean that the collector current equals to the reverse saturation current, which is 2 times 10 to the power of minus 17. 2 times 10 to the power of minus 17 amps times e to the power of VBE over BT, right? BT is 26 millivolts. Okay, so let's call this equation number 4. And well, as we can see, actually the equations 3 and 4, we have 2 variables and 2 equations. So we can find the values of VBE and IC using this system of equations, right? And yeah, that will be easy with a calculator. So let's put here using equations 3 and 4. We have the system of equations and we can find VBE and IC, right? Since we have these 2 variables in these 2 equations. So using the calculator, we can say that base emitter voltage equals to 0.833 volts and IC equals to 1.67 milliamps. Okay, so we have found BE, and that's what we wanted to find, right? Since our main objective was to work with this expression number 1, and this expression involves these 2 variables, right? And we have already found this one, BV. We now need to find BC. Okay, so now let's work with BC. Let's do it here. BCE. Okay, if we want to find BCE, what we can do is to do another KVL. Let's call this KVL 3. This KVL we go from this ground all the way through this resistor and through the collector emitter junction to ground again. Okay, so let's start. Point 1, this KVL 3. And KVL 3 is telling us that we need to first start in this ground, go all the way here first. So this will be minus 2.5 volts plus the voltage drop across the RC resistor, right? So it enters a positive terminal and goes to a negative terminal, the loop. So plus the resistance times the current flowing through the resistor, which is IC. And then the last voltage drop will be BC, right? The loop goes all the way to ground again. Plus BCE equals 0. That's our KVL. So now we can isolate BCE without any trouble. Okay, let's say that BCE equals to 2.5 minus RC times IC, right? And well, we can plug in the values of IC that we have previously calculated and RC, which is the unknown variable of this problem, right? So let's just say that BCE equals 2.5 minus RC times IC, which is 1.67 milliamps times 10 to the power of minus 3. You're right, I'm just using this value. Okay. 1.67 times 10 to the power of minus 3. Okay, so we already have this equation that we can work with. We have BC in terms of RC, which is what we wanted. Let's call this let's call this previously calculated value as equation 5 and this as equation 6, right? And well, we already have VBE as a constant value and BCE in terms of RC. So we can plug BCE and VBE inside this equation and then plug this value inside this expression. And that way we will be able to find an expression that only contains RC, and we will be able to find it, right? So now let's use all the equations we have found until now. So let's say using equation number 1, which is the this expression, right? Using equation number 1, expression 1, expression 2, this one, which is also necessary, expression 5, which is this variable, and expression 6, right? Expression using 1, 5, 2, 5, and 6. Using these equations, let's just start with 1, right? Let's start with 1. And 1 is telling us that BBC has to be less than 0.2. So then let's work with expression 2, which is telling us that, well, let's not do it like this. So let's just first use expression 1, which is BBC has to be less than 0.2. And then according to expression 2, BBC is equal to this, right? So we can just plug these two values inside BBC. So now I am using equation 2, and I can say that BBE minus BCE is less than 0.2. And well, we have calculated the BBE 0.833, so we can just plug that in, being that equation 5. So 0.833. And yeah, so BCE, we have calculated that before, and we can just plug that in, right? Minus 2.5 minus RC times 1.67 times 10 to the power of minus 3. And that will be less than 0.2. And we can see that we only have one variable and one equation. So we can now find the value of RC required in order to meet this initial condition. So, well, you can just work with this expression. So let's solve this. We can first say that 0.2. This is 0.833 minus 2.5 plus RC times 1.67 times 10 to the power of minus 3 is less than 0.2. And we have that RC has to be less than 0.2 minus 0.833 plus 2.5 all over 1.67 plus all over 1.67 times 10 to the power of minus 3. Okay, so we keep solving this, and we have that RC has to be less than 1117.96 ohms. And okay, so this means that the maximum value RC can get in order to meet this forward bias condition of the BC junction, the maximum value of RC is this, right? Since RC has to be less than this value in order for this expression to be true. So we can just say that the maximum value of RC is RC equals to 1.12 kilo ohms. And this will be the final answer of the problem, right? This is like, I'm just doing it this way. Let's highlight this with another color. Let's say this one. Okay, so that will be the final answer, that the RC required is 1.12 kilo ohms. Okay, that will be the whole problem. Yep, here we have it. Okay, so that concludes this exercise.